Okay, super. So good morning, everybody, and thank you for the introduction. And so yeah, so today's this is our a webinar that we're running on using simulation training in linear accelerators. And so and what we're trying to do here is really is to link learning and leadership. So leadership is important. There are the medical field today is got lots of challenges with staffing and with the pandemic kind of ending. There's lots of needs that the world has for better medicine, and what we need is our leaders. And so this is what so John F. Kennedy said: leadership and learning are indispensable to each other. And this is really what we're trying to do at Linax, is to empower through knowledge, empower confidence and leadership through understanding our some of the more important tools that we use in radiation ecology. So linear accelerator is the key device, and we feel that there could be, there could be better knowledge about them, which would help people to become better leaders. And our industry needs leaders. So I think most people understand that in a lot of radiotherapy departments, there are staffing shortages. The RCRP has talked about the need for universities, both at the undergraduate and graduate level, to increase awareness about radiation-related fields. And there's also a large retirement coming, where a large number of people are going to be retiring from the workforce shortly. So in Canada, 45% of the people who service linear accelerators are slated to retire in the next 10 years. And if you talk to people at the front lines, everyone talks about staffing shortages. So how do we do this, and how do we train people? Well, the traditional way of training, like the normal way, the way that we do it normally, it's kind of like apprentice-oriented training, and this is really for this webinar, we're talking about linear accelerators and servicing a medical physicist residency and so on. But this really applies generally in a lot of medicine, and really in many other fields as well. The idea of the apprentice-oriented training, so you have apprentices, you're learning on the job, and you're learning from someone who has acquired skills over a longer time, and who's kind of sharing that knowledge with young people. And it works well. It's great. It's a lot of training is based on this. However, moving it into the future with kind of the needs that we have, there are some shortcomings to this approach. So it takes a long time. It's often specific to a specific area, and so and in radiation oncology, we have vendor-specific equipment, and so which is maybe useful in some contexts, but not in other contexts. You only can practice what comes up, and so and again, and with linear accelerators, sometimes there are situations that it's important to learn from, but are difficult to reproduce in the clinic. It's very expensive. Getting access to clinical equipment, especially linear accelerators, is not cheap, and there is a certain danger factor if we're training people on, and we're changing the state of clinical devices. There's a factor to be considered, a safety factor. And then, of course, we're using resources. And then, how does this lead into continuing education? So the main thing here is that it's very difficult in our apprentice programs to access a beamline in a kind of a safe, cheap, and accessible way. So this is where Linax comes in, and this is what we believe is important for the future of our field. Is basically simulation training using web-based simulators that really reproduce the important environment that we're training on. And what we focus on initially are the linear accelerator, kind of the beamline environment of linear accelerators, and in training service engineers and medical physicists. So what the simulation training provides is a safe environment where there's it's easy to access, where there's less pressure. You can learn about situations that you can't really show in the clinic, and I'll do a demonstration of that later today. And because it's web-based, it's easy to access, and it makes them more available. So it's a low-cost solution. It's scalable. By scalable, we mean that it can be it's easy to teach one or two students, or you can teach hundreds of students, and you can teach them regardless of where they're located. Safe access to a beamline. Our simulator is meant to address all the different industries, and so it's different. It's easy to address different vendor solutions. Uh, Simulation training offers very consistent training because you can simulate the same environments over and over, and we believe we can reduce the training time for both medical physicists and service engineers by a considerable amount, and hopefully it'll keep things engaging and continuous. And we are a third-party training platform, so we train on vendor-specific equipment. So we'll talk today about linear accelerators, but we don't train on a variant linear accelerator or an electrolinear accelerator. We train on on all linear accelerators. And so our courses are built to keep up with the changing technology, and we make it easy for the learners to track and manage in-house training. So our training is centrally located. It's web-based. Things like IT issues we try to make that easy by making it web-based, and we continually refresh our materials with new materials, and importantly, it doesn't rely on utilizing clinical resources in training. So it's something that's available. You don't have to worry about Linac time or using other clinical resources. So this is what our platform looks like, and we'll talk, and I'll show you the simulator part today later on. So we have we have a simulator of both a variant style and an electric style linear accelerator, and we simulate the beam line of the system. So how do you change the configuration of the machine, the current voltages, components, and so on? How are they configured in order to produce the clinical parameters that matter to the beam? So the profiles and the depth doses, and I'll show you that later on today. We also have, a fairly extensive learning platform with many materials, and we have quizzes and labs and so on that kind of help supplement the knowledge that you need in order to kind of operate the Linux accelerator. And then we have our learning management system that's all integrated together, where you set up classes, you can assign licenses so people can access the platform, and then manage quizzes and labs and so on. So it's easy for the instructor to set it all up. So essentially we have two types of products, which that we sell. We have our in-house training products, and so these are meant for people who want to use our platform as a training platform, but they want to teach it themselves. So kind of like when a university professor has a class and they want to teach from a certain textbook, and so the students will buy the textbook, but the instructor for that class is still doing the teaching, but they're using the textbook as a resource. So similarly, we offer like teaching resources, which we configure and people can purchase on their own. We also offer instructor taught courses to service technicians, and so these are very specific towards towards learning how to service and maintain linear accelerators. So this is we have an instructor that kind of leads this. There are 26 sessions. They're each 1 hour, and they're offered 2 hour in 2 sessions a week. So it's easy to use these and not kind of have that interfere with regular work. So you don't have to leave your work. You don't have to travel, and it's all based on our simulator SIMAC, and it includes access to all our learning resources and our quizzes and labs, and it includes platform access for a year. So the benefits of our training, so it's consistent training. We believe it reduces the training time, which is important, and so which reduces training costs. Reduces the need to access a machine during the training. And then you don't have to really, our training platform is really available without needing to kind of take away from your clinical work in order to build a training platform. We built it for you. It's accessible anywhere in the world, so you can have even training, whether we live in Canada and British Columbia, but whether you're in North America, Europe, South America, Africa, anywhere, it's the same training everywhere, and it's very scalable to any class size. And we pride ourselves on saying that we can train people who have no Linux experience, but we also have materials which is important for people who have more quite a bit of experience, but also need some sort of continuing education. Where where Linux has been applied, so we now have our training platform that's been used in over 20 institutions, and it's been used in residency, the QA rotation and the residency program for medical physicists. It's used in graduate teaching for graduate students in medical physics. We've taught service engineering teams about on the professional aspects of their training and regulatory training, and we offer this as a continuing education platform. We've offered this for Linux servicing teams that are hiring new people and need to onboard them, and also for people who are more senior and want to learn more troubleshooting and resource tools. So now what I'm going to do, so now that I've introduced the platform, what I'm going to do is I'm just going to talk a little bit about how the simulation training can be used to kind of study kind of a new way of doing quality assurance measurements for some of these for different type of Linac, for some of these O-ring Linacs, so like halcyon machines, or some of these some of these a tomotherapy type machine that has different environment. So I'm just going to introduce this by talking about this paper over here. So this is a paper that was published in Medical Physics just a couple years ago, and the problem that people in this paper were trying to solve was, how do you do a good dosimetry on a machine that's an inline machine that doesn't have enough space within the bore in order to fit a water tank. So they're looking at an alternative approach to verify the 6 MV FFF beam dosimetry for an ethos machine. So an ethos machine is it's a new style. It's an O-ring machine. It's not a C-arm gantry, and you don't have enough space in order to fit a water tank onto the machine. And so the problem that they're trying to solve was that the water tanks were too big for the new ring gantry Linax, and they wanted to use 2D arrays as a ways of replacing water tanks. And so how do you do that if you can't? So how do you quantify things like beam energy if you can't measure a depth dose? Well, just to show you here, so the problem that they're facing is they want to quantify the beam energy. The depth dose is a standard way of doing this, but their equipment that they could fit into the Linac really didn't allow them to measure depth dose easily. So they looked at profiles. So basically, this is kind of two figures out of the paper. And what they did is, and I'm going to reproduce this in a second here using our simulator. What they did is they configured a true beam linear accelerator for different beam energies, and they did that by changing the bending magnetic current, which changes the beam energy, and this changes the profile of the FFF beam. And they showed quite nicely that you can get very different profiles, which you can measure the differences between these two, which are more sensitive to beam energy changes than the depth dose changes, which is the normal way of doing this. So what I'm going to do now is I'm just going to bring up our simulator over here. So this is this is our platform. So the platform it's a web-based platform. The address for it is linax.ca, and as I said before, it's designed to run without any kind of needing any special software. All you need is a good web browser. I'm using Chrome right now in order to show you, but it works with Edge, Mozilla, Safari. And when we come to the browser, our simulator is over here. So if you click on Simac over here, you can go to our simulators, and I'm going to go to our Simac 2 simulator. So I've got that set up over here. So I'll just very quickly, I'll just run through kind of how the simulator works and how how we've designed it. So this is a simulator for the beam line for either a variant style or an Electa style linear accelerator, and I've got over here the variant style machine. And so what we do here is we allow the user to kind of enter different parameters, which will configure the machine in a different way. So we have a bunch of numbers that come up on our screen, and these numbers all represent different things, that configure the machine. And in order to keep the interface simple, what we did is we left the numbers there without labeling them. But if you hover over the number, then it tells you what that is. And so this number here represents the grid voltage on the gun, and you can then change that if you want to. This number over here represents the RF driver power to the klystron, and this number over here represents the klystron pulse voltage. Some of these numbers are entries, so we can change this. Some of these numbers are results of calculations that are, or you have to go somewhere else in order to change that. So in this case over here, I'm simulating a 6 MV beam. We have some presets, 6, 10, and 15 MV. And what the simulator does is we've pre-configured some parameters. So here's the DQing on the high voltage section. We have a grid voltage. We have a bending magnet current, and so on. And this leads to an energy of beams of about 6 MV, which is exiting the accelerator, and then about 6 MV, which is striking the target. And the two aren't necessarily the same depending on how you configure the machine, and I'll talk about that in a second. So what the simulator does is it allows you to kind of simulate, the different areas of the machine, and you can focus in on different, the high voltage area. You can focus in on the gun and the injector area. You can focus in on the steering area where you steer the beam. You can focus in on the treatment head area where you can change materials. You can change target materials. You can change target thicknesses, flattening filter shapes. And the output of the simulator is a photon beam and its properties. And so here, this is the depth dose that the simulator calculates for this beam. And then on both the steering and treatment head screens, we also show you profiles because we can change things in these screens which affect the profiles. So just to show you so in the paper over here that this group did, I'll just move this over just to remind you. What they did was they varied they kind of varied what would the profile of a flattening filter-free beam look like on a true beam when we're varying the bending magnet current in the bending magnet. And so what this does is it changes the energy of the machine of the electron beam that strikes the target. So I'll just come back over here. So what they're doing in this case is they're varying the bending magnet current that we have over here. And as we change the bending magnet current, because the bending magnet acts like a spectrometer, it'll allow a different energy that they'll go through and strike the target. So in the 6 MV mode that we've defaulted over here, the Linac is making a 6 MV beam, and the bending magnet is configured to allow a 6 MV beam to strike it, and so this is balanced. However, it's possible for this to become unbalanced. So what I'm going to do now is I'm going to show you that we can take this configuration and change it from a flattened beam. So if you look at our treatment head screen, we see that these are our profiles that we're predicting. So we have a flattened beam, and we have a little flag over here, the flattening filter free flag. I'll check that, and then this is going to now simulate what the same beam would look like if we didn't have a flattening filter and we had an unflattened beam. So this is going to run now. So our simulator takes about 18 seconds to run, which is about 18 seconds longer than we want it to be. And we're working hard to kind of improve that. And the reason it takes so long is because it's doing it really is recalculating all the properties of the machine that create this beam, including the electron energy properties and then the photon beam properties. So that's finished now. So now we have our flattening filter free beam over here. And so what I'm going to do is I'm going to go in and show you. I've saved some states that I've made before. So one of the states that I'm going to load in here is a 14 MV, a 14 amp state for the bending magnet. So now if I click this, so now I'm going to go and I'm going to I'm just going to make sure that we have the right grid voltage and bending magnet current. So I'm changing the grid voltage because what this will do now is this will allow more electrons to be liberated from the gun when the machine's working, which will decrease the beam current because the electrons now there's only a limited amount of accelerating potential to accelerate them. So with more electrons, they have to share that equally, so the energy will drop. And then I've also dropped the bending magnet current in order to compensate for that. So if I run this beam now, if I run this simulator, what will happen is the energy that the accelerator is going to calculate is going to change. And so we'll see. So we'll let it finish. We'll let it run for 20 seconds. So now the accelerator is calculating 4.95 MV energy, and the bending magnet has been changed to allow the whole 14.95 to come through. If I had not changed the bending magnet current, what would happen is the dose rate would most of the electrons would not get to the target, and the dose rate would drop to 0. And I can easily show that just by going back to here and typing in the original bending magnetic current that we had, and rerunning that. So if I run that again, now the bending magnetic current it wants to let a different energy beam go through. It wants to let six MV beam energy MeV electrons go through. None of them get through because the accelerator is making 4.95, and the dose rate goes to 0. So I knew it. So I knew ahead of time that it was that how to set this up, because I calculated this before. So I knew that in order for when I reduced the bending magnetic current to 14, it was going to reduce the photon the electron beam energy, and so then I had to change the grid voltage on the gun in order to compensate for that. So now I've reset that now, and then if we go to our photon beam screen, uh, sorry, our treatment head screen, we see that we have a new profile that we've created for this. So the question then is, how does this affect the beam energy, and how do we quantify that in terms of the beam energy, kind of distinguishing between the beam energy of, let's say, the normal beam, which is the normal 6 MV beam, which is at a 16.6 amp bending magnetic current. And so we have our photon beam screen over here, which shows you our depth dose curves, and we can go now and look at the difference between the depth dose curves over here, because we calculate using our beam model, which is essentially a very similar beam model as to the ones found in planning systems, what the depth dose curves, how that would behave, how that would change. So what I've done over here is I've gone and I've done all the different modes, and so rather than going through each one individually, I'll just show one more just to show the difference. So just as an example, we have our photon beam screen here for our 14 MV beam. We have a depth dose of 68% at 10 centimeters. If I go back and if I change this now back to the, say, 17 amp state, which is a higher beam energy. So I'm just going to go through and then re-enter these to make sure that we have the correct energy. And so now if I run this, so this is the energy here is going to be probably about, if I remember correctly, 6.5 MeV or something like that. So let that run, and then what we can do is we can look at the effect this has on the profiles, as well as on the depth dose. So now, so it's a little more than 6. We can then, again, on our photon beam, our depth dose has changed a little bit. And then the profiles has also changed a little bit, but it's difficult to kind of quantify what that is. I'll just go and I'll do the next one over here. I'll go to 18 MV, which is the highest energy, or 18 amps, which is the highest energy that I've tested. And then I'll run that. And then we'll see, and then we can see again the difference. And what I'll do, and then what I can do is I can show you all these profiles superimposed together on our. We have a little water tank simulator, which kind of allows you to look at that the same way that you would if you were doing this experiment on a Linac with a real water tank QA device. So now we have our photon beams in here. So now the depth dose has changed a little bit again. But then we look at when we look at our profiles will be a little bit different. The question is how much different, and can we quantify that? So if I go to our water tank screen over here, which is the output of the simulator. So now these tabs over here simulate kind of the operation of the accelerator, and kind of what the result is. Water tank screen now simulates the QA device, and so which in this case is a standard water tank that you'd use for annual QA. And so so what we can do is we can kind of pull in some beams that we've measured before, and these are the beams that I've created, and then we can do profiles either cross plane, in plane, or depth dose profiles, and then we can label these and we can review them afterwards. So I've done that. So if I come on over here and I look now at so these are the profiles that we've measured. So here is a profile for our for the cross plane profile for the 14 amp bending magnetic current. Here are the ones. So I have the 15 amp, 15.8, 16.6. We have 17. And then 18. So these are the profiles. Normalize them so that they're all have the same central point. We down over here we give some kind of some numbers on them. So we calculate flatness. Although in the case of a flattening filter-free flatness, the flatness is kind of different than we'd expect. On a flattened beam, we'd expect this to be all at around 1, because we want very small deviations in flatness. For these beams, the flatness is very different because they're by definition they're unflat, and you do see some number changes that we calculate. This is just using a standard flatness calculation of the maximum dose minus the minimum dose within the 80% range of the profile. And so you can see we do calculate quite different numbers, which are quite a bit different than you would have on a depth dose a depth dose measurement. And so and then just to compare this now with the results of the paper that they did, again quantifying the differences in profiles that you would get from different energies from a true beam machine. And so we see this. So this is the results they have over here, and this is what we can simulate over here, and which agree quite nicely. They look very similarly. And the idea, so the point of the simulation is that in a teaching environment, it'd be very difficult to reproduce the experiment that the people who published a paper from Washington University did, just because of you have to change parameters on the machine that you would normally want to do. That changes the clinical configuration of the machine. It's not something that would be an easy thing to teach. Whereas with a simulation training, the idea that the profile that you produce is very dependent on beam energy, which again makes it easier in a machine like a Halcyon or a radiotherapy or a Meridian machine, the MR Linac by ViewRay, which is an O-ring type machine. It's much easier to measure a profile using a 2D device and then using that in order to quantify energy. So what we can also do is I can go back and I can undo these and I can say, well, what about the actual depth dose changes? Could we look at those? And so I have these over here. So we have depth dose. There's 1, 17, 18, 15, 16, and so on. If I normalize these, this is the difference in depth dose that our simulator calculates, which is pretty close to what the difference would be in a real life scenario when you change the bending magnet by these amounts. And the point of the paper was that it's much easier to quantify energy changes using a profile and flatness than it is using depth dose. And you can and so their results over here look like this. So you have these numbers, these profiles, which are all kind of together, and then our simulations simulates similar things. But just to take this one step further in terms of simulation, what we can do is we can go back and we can say, well, what about just regular beams? So this is for a machine that's a flattening filter free beam. What about if you have just a normal beam with a flattening filter? Or what happens then? And is there anything to learn there? So what I'll do is I'll go back to our treatment head screen. I'm going to put the flattening filter screen. I'll put that back. I'll run this. Now, immediately what we're going to see is that the flatness that we get is going to be very, very different, because what we've done is we've taken our simulator in our 6MV mode, and we have taken the flattening filter away, and now we've changed the beam energy. And the beam energy now, what we've changed it to is around 6.5 MV. And then, of course, so now we have a higher beam energy. The beam energy is still striking the flattening filter that we use for a 6 MV beam. And so the attenuation is going to be very different, right? And we can see this here on our profiles, where on our D max profile over here, the beam is more intense at the center and less intense at the sides, because the flattening filter is not designed to attenuate that unit to a uniform distribution. So again, it's the same thing. What I've done is we can go through, and then I can go and I've configured some beams over here. So here is a 14 amp um, um, bending magnet current with including a flattening filter. So if I go back and I just load this into the simulator now, and this is so I can easily rerun this now, because it's a simulation. On a real machine, teaching the same thing would be very, very difficult, because this would be a lot of there'd be a lot of work to first of all make sure that you're doing this safely, and then you'd have to undo it afterwards and to make sure that you weren't changing the properties of the machine. So now we have a very low energy beam over here because we've dropped the bending magnet current quite a bit. The beam energy, I've configured the grid voltage in order to reduce the energy, and then that's matched with the bending magnet. And when we look at our treatment head screen now the profile looks again quite a bit different now. And now in this case, it's over attenuating at the center and under attenuating at the sides because the flattening filter is designed for 6 MV, not about 5 MV, and so it attenuates more the 5 MV beam than at the center. At the sides of the beam, the flattening filter is very thin. It really the flattening filter doesn't have much of an effect, and so you kind of have this kind of strange shape like this where you have an over attenuated beam at the center. And again, so what I've done now is I've gone through and I've done different energies, and so I can go back to here. This is the 16.6 amp beam. This is essentially the configuration for a 6 MV beam. So this goes back and we're going to regain the 6 MV beam, which is the one I started with. So I can run the simulator, and we can do that, and then I can just to show you that that we can recover the the same beam that we started with. So let's run. Go back to our treatment head screen now, and we have oops, that put the flattening filter back in. I'll take that out. And so now that's come out. So now we've recovered our flat beam. So what I can so then I so again going back to our water tank, we can go back and we can look at these now. So I have we have the profiles for these for the different for the different bending magnetic settings, including a flattening filter. So here we have. So I'll just pull these up. So we have 15.8, 14, 16, 6, 17, 18, and so on. And so now we see over here. So which one is funny? The cross plane. So here is the so again we see some of the beams. The one with the 18 amp bending magnetic setting is the highest energy beam. So this one has the profile has the highest intensity at the center and lowest at the sides. And then the other the green beam over here is with the 14 amp flattening filter setting, which is the lowest energy, and its flatness is very different because it's lowest at the center and highest at the sides. And then if you look at the actual flatness numbers over here, now these are the ones where it's essentially the 16.6 is a nominal beam. So 16.6 has a very low flatness, but the other beams have higher flatnesses because they are of the mismatch in energy between the photon beam energy and how the flattening filter was designed. So again, in simulation training, you can teach this, and it's been quite widely known for many years that flatness and beam energy are correlated, but it's very difficult to demonstrate that on a clinical machine. So the idea behind simulation training is that it simplifies that, and it allows. I think I have the wrong one here. That's better. And it allows both the teacher and the person who's learning to see things and to understand it in a different way. And now you can go back and study the photon beam theory. So why is this causing this? So that's because of the directionality of the beam, which you can see over here. So on our treatment head screen, we also plot the spectrum that comes from the photon beam that we calculate, and we also plot the intensity angle relationship of that beam. And as you increase the energy, these beams become more forward directed because they're high energy beams. And then you can go and read through in our course space over here, which is where all the learning materials are. You can go through and read this, and you can read, we have it all explained over here. Why how the photon beams are their properties. How and why you have certain why beams behave in a certain way and how you attenuate them. So the theory is all there, and this relates back to the results of the simulator. So we have that over there. So this is just a short demonstration. So the idea behind this demonstration was to kind of show, how teaching can evolve, in a changing world. So we have over here, this is, going back to this paper, the idea of, we have new equipment in the clinic, and we have to maybe change the way we do quality assurance for this. how do we teach that? This is, it's not so easy to do it using the traditional methods, the traditional apprentice-based methods. But hopefully, with simulation training, we can kind of, we can, teach in different ways, and then people can learn in different ways, which will then allow, people to move on. And as we said in the beginning, maybe, kind of show some leadership in this area, and to take the fear out of some of these new techniques and new machines away, and let them benefit patients the way that they should. So that's our simulation training, and then so that's essentially all I have today. Hopefully, there's some questions. I'd be very happy to answer them. This is our team. So as Quinn said, I'm the founder of the company, but there's a whole bunch of people behind this. So Quinn Bartlett, our general manager, who introduced me. Matt Blanks is one who makes our webpage happen and puts everything there. Root and Jonah are scientists. We don't have a picture of Jonah. We need to get one. And so Root and Jonah are the ones who build all the models for the simulator, and that we put there. So thanks for listening. What I'll do is I can continue sharing my screen, or I can stop sharing. Maybe I'll go back to somewhere, and then if there's any questions, I'd be happy to take some questions. And I think, Quinn, you're muted.
Yep, makes sense. I was just saying, yeah, I'll just leave this up here for a second if we have any questions coming through. And so thank you guys for attending the webinar. If you would like a team demo, quotes, or additional information, please email any of these emails. And then I also will send out a recording of this webinar if you'd like to share it around to anybody. So like Marco said, happy to answer any questions. And again, thank you guys for attending.